Hit the recording. Okay. Okay, so good morning, everyone. It's and good afternoon for some of you. So we're excited to get back with the Bish Bash LatAM meetings. I'm gonna just do a little overview of what the Bish Bash, the LatAM Bish Bash is, and what the current state of things, and what are we trying to do. And then we are going to have the very interesting talk from Carlos Cancino. So many of you probably already been in some of these meetings, but just for those that are new, this is a set of informal networking meetups that have the goal of bringing together the Latin American audio community. And by audio, we mean anyone that's working with audio, like signal processing or machine learning or like in more production, students, industry researchers, academic researchers, just like anyone that is doing something remotely related with audio research. This is like the Bish Bash is a series of networkings in general. It's not only for Latin America, there are others in San Francisco and Tokyo and other cities and places. So we thought it was good to take this to Latin America because it turns out that there are a lot of labs and research is spread out, and we need to create this networking to be able to share our work, to know what's going on, to give visibility to all of these researchers and students, and to also have like our own network. And we had a series of meetups in the past years, mainly 5 meetups before this one's hosted around in different labs. In this case, it was like the first one was in Sao Paulo, hosted by Unicampi, then Montevideo, hosted by UDELAR, Bogota, Rio de Janeiro, and Mexico City. And it's kind of like we rotated these meetups and had presentations from researchers in these different locations. And now we're shifting to a different format in which we kind of have meetups with presenters, and we'll have also some sessions of like feedback from students. But this is more or less what's been going on with the meetup. And the meetup is an initiative that is sponsored by the IEEE Signal Processing Society, in particular the Audio and Acoustic Signal Processing Technical Committee. The current organizers is basically me, myself, and Magdalena Fuentes. I'm an assistant professor at NYU. There's also Andres Ferraro from SiriusXM or Pandora. And we are very lucky to have a cohort of student organizers that are doing a lot of amazing stuff, that are Giovanna, Bernardo, Carlos, and Braulio from all over the place, like NYU, UFRJ, USP, and UDELAR. And the idea is that this is going to be, we're going to be organizing this for the next year, and then this is going to be rotating for members of the community that are interested in helping organizing this. And just as an overview of what's going on, what's going to happen next year with the meetup, we are planning 3 online meetups, which will be in the same format as today, which is there's going to be a main talk, then a Q&A session, and then breakup rooms where we can discuss certain topics and like a half an hour discussion and different, and a little bit of networking. We are also planning to do one of those 3 online meetups, maybe more oriented to students and giving feedback on particular things, or discussing some topics that such as like applying to universities, or how should we my CV, or like is my presentation correct, or like give feedback on my topic of research and things like that. And the nice thing also that might happen, or like we're hoping it will happen in next year, is at the end of the year, we are trying to organize one in-person meeting that will span a few days, and it's sponsored by the IEEE SPS and also the Izmir community. That's also very nicely pushing for a Latin American music information research community. So they're also helping us out with that. And it's going to be probably hosted in Rio de Janeiro, very kindly by Uwe Verjota and Chris Wagner and his team. So this is a little bit of an overview. I'm not going to spend more time. I'll just let Andres introduce our speaker.
Thanks, Magda. Hi, everyone. Thanks for joining us today. I'm very happy and excited to present Carlos Cancino-Chacón, that will talk about expressive artificial musical co-performers, the accompanying story. Carlos is an assistant professor at the Institute of Computational Perception at John Kepler University, Linz, Austria. Before this role, he conducted research at the Austrian Research Institute for Artificial Intelligence, and he was a guest researcher at Ritmo in Norway. His work revolves around developing machine learning models that understand the way humans perform and listen to music, with an emphasis on 3 topics: computational modeling for expressive performance, real-time human-computer interaction in musical context, and cognitively plausible machine listening. He holds a PhD in computer science from JKU, a master in electrical and audio engineering from Grants University of Technology, and a bachelor degree in physics from the National Autonomous University of Mexico, and a bachelor degree in piano performance from the National Conservatory of Music of Mexico. So without further delay, I will give the floor to Carlos. The mic is yours.
Great, thank you. Thank you, Magdalena and Andres, for the kind introduction and the invitation. Perhaps can I share my screen?
Yes, you should be able to. You can stop.
Okay, so then this should work. I hope that you can see my slides, right?
Yes.
Okay, great. Well, thank you everyone for coming here. I'm Carlos, and well, I will talk about our journey developing expressive artificial musical co-performers. And so before going on, I want to give a shout out to all of my collaborators, because this is joint work with many people across many years. I was asked to introduce some of my research and how I got to be here. So I'm originally from Mexico. I was born in Mexico City, and from a very early age, I was an avid consumer of music and technology. And so when I was in elementary school, I started to learn the piano, and I started going to the children's program at the conservatory in Mexico City. And well, in high school, as many of you, I had a rock band, and I thought that we were very good. We were not, but I got really interested in recording technology, and I even managed to convince my parents to fund some of my early home studio and equipment. And so since I was always interested in both science and music, I decided to do both a bachelor's degree in piano performance at the conservatory, and at the same time a degree in physics at UNAM. And since what I wanted to do is actually combine both things, that led me to Graz University of Technology, where I pursued a degree in electrical engineering and audio engineering, with the original goal to go into musical acoustics. But luckily, I learned about more of signal processing and machine learning there. And then I learned about music information research and the group of Professor Gerhard Widmer at JKU in Linz. So that led me to pursue my PhD there, where I started working on models of expressive performance. After my PhD, I was a postdoc at the Austrian Research Institute for AI, also working on a project by Professor Widmer. And then in 2020, I was a guest researcher at Ritmo for a variety of reasons. The original plan was to stay in Norway, but then COVID happened. And then I got offered a position as an assistant professor at JKU, which is why I came back. But I actually spent half of the time in Oslo and half of the time in Vienna. I'm actually right now in Oslo and not in Vienna. But yeah, so well, my work focuses on three main topics. So cognitively plausible machine listening, so focusing on problems like aligning performances to scores, but also on developing models that kind of simulate the way that we humans listen and perceive musical signals. So models of expressive performance and kind of the combination of both human-computer interaction, in particular developing systems that allow people to experience and interact with expressive performance. So this is kind of the overview of the talk. I will start with a small introduction on modeling expressive performance. Then I will jump into human-computer interaction and accompaniment systems and the companion. And finally, I will talk about probably the most interesting thing of the talk about artificial togetherness in music. So in this talk, I talk a lot about different kinds of things, but in terms of music, I'm focusing more or less in notated music in the Western classical tradition. So a lot of these things could be applied to other traditions, but at least I'm focusing on clearly notated music and a lot of piano music, because as we know, piano is objectively the best instrument. Okay, so we all know, just to have basic exposure to music, so we can recognize when a performance is expressive or is human-like. So if we hear just a machine performing music, we know immediately that this is not the way a human would play music. But to motivate this discussion a little bit, I will present you two excerpts, very different but very good performances of Liszt Hungarian Rhapsody. So in these performances, I want you to focus on the differences in tempo, so how fast and how slow, and dynamic, so the difference in contrast in loudness of the two performers. So evidently, these are two very, very good performances. The question is whether we can quantify the difference between these two performances, and the answer is to some extent yes-ish. So the plot on the left compares the tempo of the two performances. So the y-axis is tempo in beats per minute, or BPM. And so the blue line represents Tomcat's performance, so it's more constrained, whereas Bugs Bunny's performance is a lot more dramatic, has more variation. A critic of the cartoons described that as a galvanizing burst of dramatic energy. And so on the other plot, we have also the same comparison, but for loudness, quantified here by the normalized energy of the audio file. And again, we see that Tomcat's performance is a lot more restrained and so less dramatic than Bugs Bunny. So this is kind of an example of how certain measurable, quote unquote, aspects of the performance can be used to explain, so the way that humans, musicians, shape expressive performance. So what we know then is that the human performance is really not an exact mechanical rendering of the notes in the score, and that an expressive performance involves interpretation of the music in terms of its structure, but also in terms of its affective content. And performers communicate not only the intentions of the composer, but also their own intentions. And this interpretation is conveyed to the listener in terms of local variations in these so-called expressive dimensions, such as tempo and dynamics. And while intended emotion is not directly measurable, the variations in these expressive dimensions are. And well, the focus of this talk would be in expressive performance, as it can manifest through these measurable expressive dimensions. Although I have an asterisk, so of course there's a lot of work trying to quantify the unquantifiable, and some of our own work has been characterizing whatever human listeners interpret as so when they listen to expressive performances. This is a kind of a simplified framework to describe research on music expressive performance, particularly models that render expressive performances from scratch. So starting from a score, from which, so in machine learning, we would extract some features from the score, and we would have some sort of representing, a way of representing the performance in what I will refer to as expressive parameters. So numerical descriptions of whatever happens in the performance, and then we have a computational model that relates both of them, and we can get a performance from that. And from here, I will move on to a specific system that we designed a few years ago during my PhD that we called the basis mixer, which implements this basic framework in 3 parts. We have a score representation model, performance representation model, and so the computational model, which is a predictive function. So this is important because it will connect later to the accompanion. And so let's see each of these parts in a little bit more detail. So one of the big questions is, what is a score? So this is a more complex and almost philosophical question. For our practical purposes, a score is kind of a symbolic representation of the composition. And it does not only contain note information, but also other elements that provide context to the music. This also means that for an expert performer, the score implies a lot more information than from a beginner, because so you can extract all of the different information and things from the context. So it has things that are relatively easy to understand, like so time signatures that define a specific metrical hierarchy. So a key signature that specifies a tonal hierarchy, and a plethora of markings that indicate how something could be performed. And a way to capture this in some sort of way that a machine learning model could process it is what we call the score basis functions, which is kind of a general way to represent information to quantify these objects into something that can be processed by a machine learning model. In our original definition, we focused specifically on real valued functions, but nowadays you could substitute so these real valued functions for something that generates a token, for example. And so in this example, we have a score and we have a number of notes, and we can have different types of information regarding to a note. For example, for this note here, N0, we have its pitch, so it's MIDI pitch. We know that this note is being affected by this piano marking. We see that this note is not being affected by the forte marking. So it's not being affected by the crescendo, and it does not have an accent, for example. And so we can have a lot more basis functions, some that just represent things directly in the score, and some things that can be derived or even learned from lower level representations. And the main idea is that you can put everything together into a matrix where each row represents a note and each column one of these basis functions. And this is the basic score representation. Then moving on to the performance representation model. So this is, there are multiple ways that we can represent and capture a performance. And the way that we do it kind of depends on the specific application that we want to use. And in this case, I'm going to describe the performance representation model that we are actually using later in the companion. So in here, we have a piano roll, but instead of the usual MIDI pitch, we have the MIDI velocity here, since we are matching with each of the notes in the score. Right, so each of these blocks represents one of the notes in the score. And so for modeling dynamics, we divide it in two parameters, velocity trend, because whenever we hear a chord, we don't hear individual notes, but we hear just one single unit. And so then we wanted to represent the loudness or so the dynamics of that particular unit. And this is why we go with velocity trend, and we go with the maximal MIDI velocity of each of the notes. And then we go with MIDI velocity deviations for the individual notes, which basically, so we just get the difference from the trends. Of course, the choice here of the maximum value for the trend is just a modeling choice, so there can be many possibilities. For timing, we consider kind of micro timing deviations, and again, remembering that the notes in a chord are not performed all exactly at the same time. What we have is some sort of equivalent onset time, denoted here in with O hat. And from this onset time, which we can estimate in a number of ways, the way that we do it is we compute the average value of the onsets of a chord, and then we compute timing as the deviations from this average onset time. And then for tempo, for models that are generating the expressive performance, beats per minute is probably not the best unit to model tempo. Instead, we use beat period. And so notice here that I add an asterisk. So in here, what we are computing is basically the ratio between performed inter-onset interval. So here with this red arrow to the notated inter-onset interval. And so this is also defined at a specific score position. So which means that all of the notes would have kind of the same value. And articulation. So this is, of course, a lot of simplification. We just consider the ratio of the performed duration to the notated duration. And if we do this, we end up with two matrices, one for the onset level defined parameters and one for the note level parameters. And so we move to the final component. So this so-called predictive function, which is just a mathematical function given some parameters that predicts the values of the expressive parameters given the score representation. And the way that we usually model this is as a supervised regression problem, which means given a training set, we can learn the model parameters by minimizing the reconstruction error. In here, then one of the things is, well, what is a training set in this case? And we need data. So, as opposed to other domains like computer vision, we don't have like a lot of data for modeling this. And then we need to make it from different parts. For example, we could use basically automatic transcription and OMR from scores and then create automatic alignments. But given the issues with each of these components, this also not always results in very clean data. So the best thing that we have so far is using MIDI-capable instruments, so to generate the MIDI. And usually using manual transcription. Luckily, there are many repositories like MuseScore or Kern Scores or whatnot that have many of the scores in the traditional classical repertoire. And then we can do semi-automatic alignment and then do manual corrections. So the best datasets in this case for these are datasets that are collected with computer-controlled grand pianos like the Yamaha Disc Clavier. And there are a few datasets that are particularly good for these tasks, like the Vienna 4x22 dataset. So the Magalov dataset that was also collected from in our group. And well, the largest one so far, so the ASAP dataset, that is a subset of the Maestro dataset that has been aligned to its scores. The way that we did it in the original basis mixer, back then in 2016 and 2017, we used bidirectional LSTMs to model the performance, given that, so when modeling expression, not only the prior context is important, but also the upcoming context. So when we are playing something like a fermata, if we know that the fermata is coming, we might slow down a little bit, for example. And so in this case, basically what we have is our input basis functions evaluated at score level, at the score onset level, and the output would be, so the onset level parameters. And for modeling the node level parameters, we use feed-forward neural networks. And well, so this works relatively well. So this is an example, an output of the model. This is an excerpt of a nocturne by Frédéric Chopin. And so these red lines under the score represent the predictions of the tempo. So since they are predicting beat period, so the higher the curve represents the slower. And so you can see that it kind of identified some phrasing structure for the piece, even though it was not explicitly told what is a phrase. And so let's hear it. Okay, so far, the big question, and so one of the big questions for discussing later is how do we evaluate these models in the first place? So the question is how to evaluate generative outputs that produce some sort of artistic or aesthetic output. So in earlier research that focused on rule-based models, a lot of what they did was evaluation through listening experiments. Basically, they would propose a new rule and they would conduct an experiment to see if this rule made sense or not. But as you can imagine, so this is a never-ending process because there are infinitely many possible rules. And with data-driven models, the main goal is to have some sort of quantitative comparison of the recorded performances using reconstruction error loss functions like mean squared error or some likelihood. But unfortunately, in this case, reconstruction error like metrics are kind of evil because they do not really represent closeness in terms of perceptual closeness or aesthetic musical closeness. One of the big issues is how do we choose the reference performance when we are comparing the difference to which performance, right? The answer is usually to whatever we have in the dataset, but this is not necessarily something very satisfactory. And different pianists would play things in different musically valid ways. We can say that we prefer one over the other, but it's hard to say that they are not valid ways to interpret the music. Then, so the holy grail would be to create a metric that can tell us whether a performance is musically valid or not. And so the big question is whether this is something that we could try to learn with machine learning methods, which is a big open question. As an example, here I have 4 bars of a Mozart sonata. And so the thin lines in color in the bottom represent the tempo from real performances. So the shaded area represents, I think, 2 standard deviations from the mean. and the thick line is the mean. And what we have here in this thick red line is just a randomly sampled performance that is just around the mean. And what we see is that in many cases is actually closer to the mean than some of the actual performances, even if this randomly sampled performance would be perceived by a human listener as something not very musical. Right? Okay, so not giving any answer to this question, I move to the next part, talking about automatic accompaniment systems and the companion. So in recent years, there has been a lot of interest in human-computer interaction thanks of advancements in AI and machine learning. And in terms of music and music performance, this has translated into interfaces that allow people to experience music performance, let it be in terms of learning apps or learning systems, systems per se for interactive performances, or tools for music production. In here, I would like to make another parenthesis to kind of put into context how we humans listen to music and how computers listen to music. So we know that we both do things in very different ways, and where our brains are very magical information processing machines, effectively, that make sense of the auditory signals very effortlessly, whereas computers struggle doing basic tasks. For example, if someone is playing the piano, so there's a pressure wave resulting of the vibration of the strings, and our mind, basically our ear identifies this immediately as music, and we identify elements as notes and so on. Even if we don't really have a background in music theory to understand all of the complexities of the music. But for machine, this is just a signal. So this is a variation of amplitude over time captured by a microphone. And if we have people talking, we would have a pressure wave that would be different, but we would immediately identify this as speech. And if we understand the language, we would understand what is going on. Whereas for a machine, this would look kind of exactly the same. So this means that computers are basically processing signals at a very different representation level than we humans. And in many cases in machine learning, we are not necessarily trying to do exactly what humans do, like in chess, for example. But I would argue, at least in the case of music or the systems that are trying to produce an artistic output, since there's not an objective ground truth or an objective answer to this, we would really need to develop models that can identify or predict the same kinds of patterns that human listeners would perceive. And so developing this requires us to understand more about human perception rather than just trying to solve everything through computational models. This leads us to accompaniment systems. And in this case, for this kind of work that we are doing, we have artificial co-performers that are performing notated music. So all of the parts are notated. They are not generating an accompaniment part. So they are not composing an accompaniment part to what the soloist is playing, but they are playing a pre-written solo accompaniment part. And what they are is basically a computational agent that performs in real time with a human soloist and adapts its performance to the performance style of the soloist. Work on accompaniment systems started in the 80s with pioneering work by Roger Dannenberg. And in his seminal 1984 ICMC paper, he identified three main tasks that accompaniment systems must solve to perform together with humans. The first one is detecting the solo part. So whatever you are playing, identifying what are the notes or what is the musical information, which is complicated if we do this directly from audio, but we can kind of bypass this if we use a MIDI-capable instrument, which is what we do with the accompanier. The next problem is score following and generating an expressive accompaniment part. Score following is basically matching musical signals of the same piece, so a performance with its score in real time. And most research on accompaniment systems actually focuses on this particular problem. The last problem is generating an expressive accompaniment part. And as you see, this is a very similar framework as the one for solo performances. But in this case, we have both whatever the soloist is performing and the score of the accompaniment part. And we extract features from both of them, from the score and the solo. And we pass this through a computational model. So let it be rule-based model or neural networks or cognitively based sensory motor synchronization models, and we predict our expressive parameters, which we use to decode the performance of the accompaniment in real time. So the accompaniment, our system, consists of 3 components, which solve each of the problems. We have a MIDI handler, which solves the first problem, so it receives and sends MIDI messages. We have the score follower, so which solves problem 2, and we have the accompanist module, which solves the third problem. Basically, it generates expressive accompaniment. And how does this work? We have first of the scores, and so then we set the score follower to the solo part so that it knows what it needs to follow, and the accompaniment part is sent to the accompanist module. And whenever the human soloist plays something in a MIDI-capable instrument, so like this clavier pictured here, so we get the MIDI, which the MIDI handler sends to the score follower, and the score follower identifies where you are playing in the score, and this information is sent to the accompanist, and the accompanist consists of 2 modules, so an encoder and a decoder. And so the encoder encodes information from the performance of the soloist, and the decoder takes the score of the solo part, of the accompaniment part, sorry, and decodes the accompaniment part from this point on. And so this is sent to the MIDI handler, which schedules the MIDI messages again. And when the soloist plays a new note, we update our information and do this procedure again and again and again. And so far, this seems very nice, but something very important that we have not considered here is actually what happens to the human soloist, how the human reacts to whatever the system is doing. All of these systems are trying to think of how to adapt to the soloist, but actually we humans adapt to the system. And actually, even when all of these systems are working correctly, if this last part does not work, the results are very, very unnatural. So as a quick overview of the different components for the score follower, so we have a setup where we get our score, and we have some feature extractor from which we get some internal representation of the score for the score follower. And here is an animation of what happens in real time. So we have some MIDI messages coming from the soloist, and then we have an online input feature extractor that computes information from the performance. And we use online time warping, which is basically the real-time causing of dynamic time warping to predict the position of the soloist in the score. And so then at each point, we know more or less where we are. And this is all nice, but it's not super robust. Then the solution that we came up with is basically using a multi-agent score follower. So we have the solo performance, and then we have multiple agents. And we discovered that instead of trying to align directly to the performance, to the score, we can ask the soloist, for example, to rehearse, quote unquote, rehearse and record a few times the performance. And then we can use offline alignment methods. And basically, in real time, we are aligning performance with performances. And through the mapping that we have from these aligned performances to the score, we do some aggregation, and we can infer the position of the soloist in the score. And well, so the final part, so the accompanist, this is where we bring up the basis mixer again, because our accompanist module is basically the basis mixer in disguise. The score representation model is the same, but here our performance representation model is what we call the accompaniment, the accompanist encoder, and the predictive function is our accompaniment decoder. And in this case, since we don't really have a lot of data of duet performances, what we have is a pre-trained basis mixer model. And then if we have these recordings of the soloist that we use for the score follower, we can fine-tune the basis mixer to the performance of the soloist, and we can use this fine-tuned model to predict the accompaniment part. In the current version, for technical reasons, the prediction of the note level parameters is computed offline, and we just store it. But for the future version, we will have a slightly updated thing with real-time predictions. And well, if you remember when I described the performance representation model, I had an asterisk on how to compute the tempo. And one of the issues is that direct computation of tempo can be very, very erratic, and it does not really represent the way that we humans perceive tempo. For example, here we have a pathological case. We have a very complex rhythm, so we have 11 versus 12, and humans are known to not play things exactly as they are written. And as it happens here, sometimes one of the order of these notes is changed, so which result in weird artifacts like negative tempo values, which do not really make sense. So the thing that we decided to do in this case is to use cognitively plausible models of sensory motor synchronization, which are models derived from music psychology, are basically combination of oscillator models, so coupled oscillator models. And we tried a bunch of them, and we even modified some of them ourselves. Basically, what these models provide is an asynchronous-based correction term that let us predict tempo and result in smoother tempo curves. And they also allow us to predict what will be the next performed solo onset by the soloist. So as a timeline of the development of this system, so in the early 2010s, we developed a lot of the basic technology at JKU, including so real-time score following and so the basis mixer as a deep learning-based model of expressive rendering. The first version ever of the companion actually came out in 2017 for a competition organized by Dartmouth University. And we won a $500 award. No, it was not the first prize, but still, it was a $500 award. It only worked for monophonic music. So the second version came out in 2019, and in this case, we expanded the capabilities using an HMM-based polyphonic score follower. And so this worked okay, but it was not very robust against human errors and complex music. And this led us to the current version, so using online time warping. And so we won an award at the Falling World Science Summit in Berlin in 2021. But still, so even if it works better, it's not perfect. Our goal then in the not so distant future is basically to have the system to be able to play something extremely complex, so like Rachmaninoff's Third Piano Concerto, with professional musicians in real concert settings. If you know professional musicians, they would not really like to play with something that can fail. They are not very happy that if something could fail, then they would rather not play with it at all. So this is our goal. So as a demonstration, this is a video of myself playing with the system, recorded at the Bessendorfer Salon at the Musikverein in Vienna. They were very kind to let us record there with a super fancy piano. So then the final part of the talk. So I will talk about artificial togetherness. And so one of the big challenges in real-time AI co-creativity, so I would say, is the feedback loop with humans. As I mentioned before, a lot of work has been done in how AI systems react to whatever humans do, but not the way that humans react to whatever systems do. And the second thing, in particular in music, is this feeling of togetherness in human-computer interaction. So togetherness is a concept from cognitive sciences that has been gaining some traction in recent years. And it refers to feelings of social alignment and connection. So it's something phenomenological. It's about the way that we experience things. And well, human experience is just very, very complex. What is true is that our systems cannot experience togetherness yet, because of course they do not have mental states in the same way that we do. They do not have explicit intentions. So their experience is just limited to whatever their hardware and software allows them to perceive. This is a framework for musical togetherness by Laura Bishop from the University of Oslo. And so there are several factors that increase the feeling of togetherness in humans. So this framework was devised in context of string quartet performances and orchestral performances and so on. So then let's see how our cute machine overlords do in this case. And so they kind of have awareness of others in a shared musical setting. So that is as long as we can extract information from musical signals. So in terms of Royer-Dannenberg's problems, so this would be problem number one. So they can interact with others. This is what they were designed to do. They cannot share higher order experiences with others, definitely not. And they can help us achieve goals as long as we can formulate the goals in terms of appropriate metrics. But as I discussed earlier, this is a big open question, and our metrics might not be the best ones. And well, they definitely do not have cognitive alignment with others. So what is missing and what should come next? Well, beside all of these tasks, I think a very important thing would be to add an extra task of trying to model the feedback loop with human partners. So not only modeling and focusing on what the systems do, but also what humans will do. And for these systems need to be more predictive and not really reactive. But the predictions, at least in real time, need to be very good because it otherwise breaks the illusion. And well, our experience is that models developed in context of music cognition tend to focus on kind of reduced scenarios like tapping and simple melodies, and do not scale that well for complex music. And MIR methods tend to focus on different things and do not really generalize, at least for this case of Western classical music, where we have variations in dynamics and tempo that depend on the structure of the music. And the other big question, as I mentioned before, is how do we evaluate these models? This is kind of the big open question. I think that the way that we can solve this is not thinking that we from so computer science and technical backgrounds can solve everything on our own. And so we should try to be perhaps less arrogant of thinking that we can just solve everything with more data and more machine learning methods. But what we need is more interdisciplinary research and collaboration with musicians and psychologists and other areas. And this is the way that we can kind of define the things that we actually need to model and where we should put our efforts. And well, just as a final thing, as a little bit of advertisement of the work that we do at our group, we have a JKU Python music processing ecosystem with a number of Python libraries, some of which might be familiar to you, so like the MatMom library. We have our symbolic music processing library, Partitura, for which we had a tutorial at ISMIR 2022. And we are preparing a new package for a number of standard symbolic music analysis tasks. This year's ISMIR, we released a library for offline symbolic music alignment. And from our work on real-time alignment, we are preparing a library for this, so which would be a spin-off of the Companion. Of course, we have our basis mixer for expressive performance rendering and the Companion, which is open source, and you can play with it and see how well it works or how well it does not work. Anyway, thank you for your attention, and here are some links. So there are a YouTube playlist with the Companion videos. And yeah, thank you for your attention.